Hi there, Mr. Sutton here, bringing you the Algebra 2 Honors 4-6 Part 1 homework solutions on fundamental theorem of algebra, focusing on solving for all the complex roots of polynomials. For the first few problems on this problem set, we're going to be identifying the number of solutions of the equation and then finding them through whatever means necessary. So on this one, since the highest power, since the degree is 4, that means we have 4 solutions of whatever variety. There might be some imaginaries and duplicate solutions in there as well, and that's okay. Now to solve this, well, when in doubt, zero it out. Let's at least get 0 on one side by subtracting that 2. And at this point, I always tried to use normal factoring first before I go to the rational roots theorem. Since I have 4 terms here, I'm thinking I might be able to factor this one by grouping. Let's give it a shot. So for the first 2 terms, I can take out a t cubed. That leaves me with a t minus 2. And then for the next 2 terms, the only thing I can take out of there is a 1, which also leaves me with t minus 2. So t minus 2 is actually a common factor for both of those. That comes out. And then I have t cubed plus 1 as my other factor. So I'm going to go ahead and factor t cubed plus 1 a little further. That's a sum of 2 perfect cubes. So I have this a cubed plus b cubed formula that I'm going to use. A plus b, a squared minus ab plus b squared. So I've got the t minus 2 that I took out initially. And now for a, I need to take the cube root of t cubed, which is just t. b is just the cube root of 1, which is going to be just 1. So we have t plus 1. And then a squared is just t squared, minus ab is just minus 1 times t, so minus t. And then b squared is just 1 squared, so that's just also 1. At this point, I'm going to go ahead and try to factor this last piece, although I'm pretty sure I can't. I never really can factor this piece of these cubic shortcuts. Numbers that multiply to 1 and add up to negative 1. Well, there's no way to accomplish that. So I'm going to go to quadratic formula to solve this last part here. So we have negative b plus or minus square root of b squared minus 4ac all over 2a. This is going to be negative 1 for that middle coefficient, plus or minus square root of negative 1 squared, minus 4 times the a value 1 times the c value 1, all over the 2 times the a value of 1. So a lot of 1's here. On the outside, we have a positive 1. Down here, this is going to be a 2. And on the inside, we've got 1 minus 4, or negative 3. And just one more little step to simplify that. I can take that negative out as an I. So we have 1 plus or minus I radical 3 all over 2. So going back and now writing my solutions based on this factorization here. For this first factor, we see that t equals 2 is one of my roots. And then for the next one, negative 1 plus 1 would zero that second one out. And we just found 1 plus or minus I radical 3 all over 2 for the third and fourth roots. Counting all of those together, a total of 4 matches what we expected in the beginning. On this problem, since we have a degree of 5, that tells us that there are going to be 5 solutions on this one. So let's go ahead and try and solve this. It's already zeroed out, so let me see if there's any factoring techniques I can use. It looks like these all have at least an x to the third power, and they're also all divisible by 2. So let me factor out a 2x cubed. 4x to the fifth divided by 2x cubed is going to be 2x to the second power. Negative 8x to the fourth divided by 2x cubed is going to be negative 4x. And then 6x cubed over 2x cubed is going to be 3. Can I factor the stuff inside here anymore? Well, let me think. If I try the AC method, 2 times 3 would give me an AC of 6. So I'd be looking for things that multiplied to 6 and added up to negative 4. Well, there's not a lot of options. 1 and 6, 2 and 3, none of that is going to give me negative 4. So I'm going to go straight to quadratic formula on this one. So we're going to have negative 4 as my b value, and then plus or minus square root of negative 4 squared, minus 4 times the a value 2, times the c value 3, all over 2 times 2 for the a value. So on the outside here, I've got a 4 upstairs and a 4 downstairs. Inside, this is going to be 16 minus, let's see here, 8 times 3 is 24. So that's negative 8 altogether in there. And then I'll just simplify that radical negative 8 over on the side here. One thing I can do is take out an I, because there's a negative in there. 8 has a perfect square in it. I can split that up into 4 times 2. And then square root of 4 is 2, so this is just a 2i radical 2. So 4 plus or minus 2i radical 2 all over 4. I can reduce all of these things now, 4, 2, and 2 by, 4, I can reduce all these all by 2. So we've got a 2 down here and a 2 up here, plus or minus 1i radical 2. So now let me write all my solutions for this. Let me go back to this factored part here. If 2x cubed equals 0, then x equals 0, because 0 cubed times 2 would give me 0. And then we also have this solution that we just came up with the quadratic formula, 2 plus or minus I radical 2 over 2. Now let's just count our solutions and make sure we didn't miss any. We're expecting 5 here. So this 0, because it comes from an x cubed, is actually a triple root, multiplicity of 3. There's actually 3 zeros for answers. They're just all the same though. And then this 2 plus or minus business counts as 2 answers as well. So 3 plus 2 gives us our total of 5. On this problem, to find all the zeros of the g polynomial function, we're going to start by figuring out how many zeros there should be. Based on this being a fourth power, degree 4, we know there's going to be 4 zeros. That's from the fundamental theorem of algebra. So let's go ahead and see if we can factor, do whatever we need to do to solve this thing. Now it doesn't look like there's any common factors I can take out of this, so I'm going to go to rational roots theorem and figure out my possible rational roots. So we're going to have factors plus or minus of 12 over factors of an invisible 1 here. For 12, we've got 1, 2, 3, and then 3 times 4, 2 times 6, and then 1 times 12. So we're going to plug all these into our function on Desmos until we find one that gives us a 0. We'll actually plug as many in as we can until we run out of either solutions or possible rational roots. So let's go to Desmos. Here it is. And let me plug in the g function. So g of x equals x to the 4th plus 4x cubed plus 7x squared plus 16x plus 12. And let's enter down to get a new entry here. Let's do g of, well, all of these possible rational roots for now. So g of 1 gives me 40. That's not what I want. G of negative 1 is 0. So let me write that down. G of negative 1 is 0. So that's one rational root we've already found. Next up, we're going to do g of 2. That doesn't work. G of negative 2. That doesn't work. G of 3 gives us 312. G of negative 3 gives us 0. Here's another one. All right, so I've got 2 so far. So it's possible that I might have another 2 that are rational roots. Let me just go ahead, and it doesn't take too much effort to plug in the remaining numbers here. So we got 4, doesn't work. Negative 4 doesn't work. 6, that gives us, actually that was 5. 6 gives us 2,000 something. That's no good. Negative 6 doesn't work. 12 probably won't work, but we'll try it. And then negative 12 also doesn't give us a 0. So we're out of possible rational roots. That means the rest of the roots are going to be either irrational or just imaginary, one of the two. So at this point, we're going to use synthetic division with the 2 roots that we did find to break this down a little further and hopefully get it down to a quadratic that we can solve with whatever method we need. So let me write out my coefficients. We've got 1 for the x to the 4th, and then this is a 4, 7, 16, and a 12. And you can do these in either order, but I'm going to go with negative 1 first. Let me do my little synthetic division line. Bringing down our first coefficient of 1, negative 1 times 1 is negative 1, plus 4 is 3, times negative 1 is negative 3, plus 7 is 4, times negative 1 is negative 4, plus 16 is 12, times negative 1 is negative 12, and plus 12 is predictably 0. Predictably because, well, we already got 0 plugging it in the function, so we should get a remainder of 0 as well. Now I could write this out as a quotient, but since these are going to be the coefficients of the quotient that I'm then going to do synthetic division on again with this -3, I'm just going to start here and put -3 in a little box next to these numbers and just kind of keep synthetically dividing. So let me do another division line and bring down the coefficient for this line now. That's a 1. -3 times that is -3. 3 and -3 adds up to 0. -3 times that's still 0, plus 4 is 4, times -3 is -12, and thank goodness that comes out to 0. I can't go any further with synthetic division because I've run out of known solutions here. So I'm going to write out my quotient now, along with the rest of this. So for the -1, I have an x plus 1 as a factor. X minus -3 gives me x plus 3 as another factor. And then my quotient, this is going to be 1x to the second power because I started with x to the fourth and I synthetically divided twice, so that decreases my exponent by 2. And then we have 0x, which we don't have to write, and plus 4. All of that equaling 0. So going through and zeroing things out, we've got x equals -1, which we already found, -3 we already found, and now we can write x squared equals -4, and then square root each side of that. So that's going to be x equals plus or minus 2i. We have an imaginary number here. So this is why we couldn't get it with the calculator, because it didn't exist to begin with. Just double checking, we have 1, 2, and this counts as 3 and 4, 4 zeros as we expected. For this problem, to find the zeros, let's first figure out how many we're expecting. Since this is 4th degree, we're expecting 4 zeros by the fundamental theorem. And it looks like I can't really use any factoring techniques on this one, so I'm going to go to rational roots theorem. So we need plus or minus factors of 8 over the invisible 1 here. Not too many factors of 8. We've got 1, 2, 4, and 8, so not a ton of them to try. But we're going to try all of them in the Desmos here if we plug in this function into Desmos. So here's my Desmos scientific calculator. Let's put our f of x function in. That was x to the fourth minus 6x cubed plus 7x squared plus 6x minus 8. And we'll just plug in all of these from left to right. So let me do f of 1 comes out to 0. All right, let's write it down. How about f of -1? Also comes out to 0. So that's 2 in a row. That's rare, but we'll take it. How about 2? Do I hear 2? Really? Also 0. Wow. Boy, we've gotten very lucky here. Let's try -2. 17. We knew the luck had to end at some point. But let's keep going. We've already got 3. There's only 1 left here. It's probably another rational one, because if it were irrational or imaginary, those would come in pairs, and there's only 1 left. So it's got to be rational. So we've got 4 we'll plug in. That comes out to 0, and there it is. So we found all 4 answers. 1, -1, 2, and 4 without doing any factoring whatsoever. Good for us. For this problem, from 1900 to 2017, the number, p in thousands of immigrants residing in the U.S., can be modeled by this function below, apparently. And t is the number of years since 1900. Using technology, we want to know in which year did the number of immigrants reach 43 million. So this is the beautiful thing about polynomials, is you can model pretty much anything, at least within a certain range, if you pick crazy enough coefficients to do it. So on this one, we're trying to find a t-value at which the p-value equals, well, they said 43 million, but p is expressed in thousands. So we would actually have to, let's see, how many thousands is 43 million? I think that's 43,000,000. So we're going to set all of this stuff equal to 43,000. Next, when in doubt, zero it out if we're going to solve this thing. So we'll subtract 43,000 from both sides. Let me go to Desmos for that. So we've got 11,757.7 minus 43,000. No way I'm doing that by hand if I can help it. That's negative 31,242.3. I will take their word for it. And at this point, the only way to solve this polynomial definitely not factorable. We're going to have to graph this thing out on the Desmos graphing calculator and see where it touches the x-axis, although I guess it would be the t-axis at this point. One thing we're going to want to be aware of as we do this, since this is a third-degree polynomial, that means we could have up to 3 real solutions. We're going to have at least one. We're guaranteed at least one because it's odd, but we might have up to 3. So we're going to have to be on the lookout for multiple x-intercepts. So let's go to Desmos Grapher, and let me put my function in now. I'm going to just call this f of x. So f of x equals 0.0757 x to the third power minus 7.893 x to the second power plus 187.10x minus that crazy number 31,242.3. And let me expand my window a little bit so I can see. And I see nothing. Well, let me zoom out until I see something. We'll just keep zooming out. Now, this function is good between 1900 and 2017. In terms of x values, that means we're going from 0 to 117. So let's just move over a little bit this way and zoom out. Ah, there it is. There's our function. Let's zoom out a little further. All right. So we can see that there's only one place this thing crosses anywhere near this range of numbers. So let's zoom in a little bit and see what that spot is. Let me just click on my function, click on this little gray dot, and it looks like that's 114 and change. So here is what I just graphed out. And they asked in what year did the number of immigrants reach 43 million? It was about year 114, so this would be 2014 for the actual year.